Welcome to today's problem walkthrough. We'll be exploring KTH symbol and grammar, a fascinating problem that challenges your understanding of recursion and binary sequences. Let's dive in and break it down step by step. In this problem, we are working with a sequence of strings that is built recursively. The process starts with the string 0 at level 1. For each subsequent level, we generate the next string by applying a specific rule. Every 0 in the current string is replaced with 01, and every 1 is replaced with 10. Our goal is to determine the KTH symbol, using 1-based indexing, in the nth row of this sequence. For example, if n is 4 and k is 5, we are tasked with finding the fifth symbol in the sequence generated at the fourth level. Given the constraints, n can range from 1 to 30, and k can range from 1 to 2 raised to the power of n-1. The result will always be either 0 or 1, as the sequence is binary. Let's look at the first example to better understand the problem. Suppose n equals 1 and k equals 1. At the first level of the sequence, we have a single symbol, 0. Since k is 1, we are looking at the first symbol, which is 0. Therefore, the output for this input is 0. This example illustrates the simplest case, where there's only one symbol in the sequence. Now, consider the second example where n is 2 and k is 1. At the first level, the sequence is 0. When we generate the second level, the rule tells us to replace 0 with 01. So, at level 2, the sequence becomes 01 foot. Here, k is 1, meaning we're looking at the first symbol in this sequence, which is 0. Hence, the output is 0. This demonstrates how the sequence evolves and how we can identify the desired symbol based on the given k. In the third example, n is 2 and k is 2. As before, the sequence at level 1 is 0, which transforms into 01 at level 2. This time, k is 2, so we're looking at the second symbol in the sequence 01. The second symbol is 1, so the output is 1. Additionally, let's examine a slightly more complex example where n is 4 and k is 5. At level 1, the sequence starts as 0. At level 2, it becomes 01 foot. At level 3, 01 foot evolves into 0110, and at level 4, 0110 evolves into 01101001. The fifth symbol in this sequence is 1, so the output is 1. To summarize the final example, at level 4, the sequence is 01101001, and the fifth symbol in this sequence is 1. It's important to note the constraints of this problem. The value of n can go up to 30, which means the sequence grows exponentially, making it impractical to generate the full sequence for large values of n. This is why an efficient mathematical approach is necessary to solve the problem. Additionally, edge cases such as n being 1, where there's only one symbol, or k being close to 2 raised to the power of n-1, require careful handling to ensure correct indexing and logic. To begin, one straightforward approach to solving this problem is by directly simulating how the sequence is generated. The idea here is to start with the initial string, which is 0, and then repeatedly apply the transformation rules to build each subsequent level. Specifically, every 0 in the sequence expands into 01, and every 1 becomes 10. After fully constructing the sequence up to the desired level, we can simply retrieve the KTH symbol. However, while this approach is intuitive and directly follows the problem's description, it has significant drawbacks. The time complexity is exponential, 2 to the power of n, because the sequence doubles in size at each level. Additionally, the space required to store the entire sequence also grows exponentially. This makes it impractical for large values of n, as both time and memory usage become prohibitive very quickly. A more efficient strategy leverages the recursive relationship between levels. Instead of generating the entire sequence, we can focus on the parent-child relationship. The key observation is that the KTH symbol at any level depends solely on its parent in the previous level. We can determine the parent's index using the formula k plus 1 ///2. The relationship between parent and child is straightforward. If the parent is 0, the left child is 0 and the right child is 1. Conversely, if the parent is 1, the left child is 1 and the right child is 0. Using this relationship, we can recursively trace back to the first level to compute the KTH symbol without ever building the full sequence. This approach reduces the computational overhead significantly while still adhering to the recursive nature of the problem. By analyzing the recursive approach, we find that its time complexity is O(n), as each recursive call moves one level closer to the base case, resulting in n calls. The space complexity is also O(n), due to the recursion stack. While this is a significant improvement over the brute force method, it has a notable limitation. The recursion depth can become problematic for very large values of n, potentially leading to stack overflow. To address this, we turn to an optimized iterative approach based on bit patterns. The key insight here is that the kth symbol's value can be determined by counting the number of ones in the binary representation of k1. If the count is even, the symbol is 0, if odd, the symbol is 1. This eliminates the need for recursion entirely and enables us to compute the result directly, leveraging the structure of the sequence in a highly efficient way. The optimized iterative approach has a significant advantage in terms of complexity. Its time complexity is O log k, as counting the number of ones in the binary representation of k1 is proportional to the number of bits in k, which grows logarithmically. The space complexity is O(1), as we do not rely on recursion or additional memory to store intermediate sequences. However, there is a trade-off. This approach requires an understanding of bit manipulation techniques, which might not be immediately intuitive to all problem solvers. Despite this, the iterative method is highly efficient and avoids the major drawbacks of both the brute force and recursive approaches, making it particularly well suited for handling large inputs. After evaluating all the approaches, the optimized iterative method stands out as the most efficient and scalable solution. With a time complexity of O log k and space complexity of O(1), it outperforms the brute force approach, which is exponential, and the recursive method, which has linear time and space requirements. Moreover, it is well suited for large values of n and k, as it avoids both the exponential growth of the brute force method and the risk of stack overflow in the recursive approach. The key insight driving this strategy is the use of bit manipulation to directly determine the kth symbol based on the binary structure of the sequence. This not only simplifies the computation but also highlights the elegance of reducing a seemingly complex problem to a simple mathematical operation. Overall, this approach effectively balances efficiency, scalability, and simplicity, making it the optimal choice for solving the problem. To solve this problem, we need to understand the recursive process that generates the sequence. Starting at level 0, the sequence begins with just 0. At each subsequent level, every 0 in the string is replaced with O1, and every 1 is replaced with 10. For example, level 0 is 0, level 1 transforms into O1, level 2 becomes 0110, and level 3 further expands into 01101001. Notice that with each level, the sequence doubles in length, growing exponentially. This doubling behavior is a key characteristic of the problem and will influence how we approach solving it efficiently. One way to solve this problem is by simulating the sequence step by step using a brute force approach. Starting with the initial string 0, we iteratively apply the transformation rule for each level. This means that for every character in the current string, we append O1 foot if the character is 0, or 10 if the character is 1, to create a new string. After processing all characters, the new string becomes the current string for the next iteration. We repeat this process until we reach the desired level and then return the resulting string. However, this approach is highly inefficient for large values of n because the sequence grows exponentially, requiring both O(2 to the power of n) time and space. To address this inefficiency, we need to optimize our solution by avoiding the full simulation of the sequence. To improve efficiency, we can leverage the recursive nature of the sequence. For example, if we need to find the kth character of the nth level, we can determine whether this character lies in the left or right part of the transformation from the previous level. Using this insight, we compute the answer recursively without generating the entire string. Similarly, if the task is to count specific characters like 0 or 1, we can use a recurrence relation to compute the counts iteratively. This avoids the need to explicitly construct the sequence, making our solution far more efficient. There are a few key insights that make this problem more manageable. First, the sequence grows exponentially, with its length at level n equal to 2 raised to the power of n. Second, the recursive structure of the sequence allows us to break it into two halves, each derived from the previous level. This property is particularly useful for efficiently calculating specific characters or properties. Finally, we can visualize the sequence as a binary tree, where each node splits into two child nodes representing 1 foot or 10. This binary tree analogy provides a clear structure for recursive computation and helps us understand the problem more intuitively. To implement the solution, we can use different data structures depending on the approach. For a brute force simulation, we use a string to store and transform the sequence at each level. However, this is inefficient for large N due to the exponential growth. For optimized queries, a recursive function is the ideal choice, as it directly leverages the recursive structure of the sequence to compute specific results efficiently. Finally, if the task involves counting characters like zeros or ones, we can use arrays or counters to iteratively compute the counts based on results from previous levels, avoiding the need to generate the full sequence. The complexity of each approach highlights the trade-offs between efficiency and simplicity. The brute force approach has a time and space complexity of 2 to the power of n, as it explicitly generates the entire sequence, which grows exponentially with each level. In contrast, the optimized index-based approach has a time and space complexity of n, as it recursively computes results while avoiding redundant calculations. Similarly, for counting characters, the time and space complexity is n, since we use recurrence relations to compute the counts iteratively. These optimizations significantly reduce the computational overhead, making the solution scalable for larger values of n. This Python implementation efficiently solves the KTH symbol in grammar problem using recursion. The problem states that we start with 0 at row 1 and generate the next rows by replacing 0 with 1 and 1 with 10. The goal is to determine the KTH symbol in the nth row. ###line by line explanation. 1. The KTH grammar function is defined as part of the solution class. It takes n, row number, and k, position in the row, as inputs. 2. The base case handles the simplest scenario, when n equals 1. Since the first row always contains only 0, the function directly returns 0. 3. For rows beyond the first, the function recursively determines the value of the parent symbol in the previous row. This is calculated using the formula k plus 1 / 2. This formula identifies the position of the parent symbol in the previous row. After obtaining the parent symbol, the function determines the current symbol's value based on the parent and whether k is odd or even, parity of k. If the parent is 0, the current symbol is 0 for odd k, left child, or 1 for even k, right child. If the parent is 1, the current symbol is 1 for odd k, left child, or 0 for even k, right child. 5. The final result is returned after evaluating the parent and parity logic. ###. Complexity analysis. Time complexity, n, as the recursion depth is proportional to n. Space complexity, n, due to recursive call stack usage. This approach avoids constructing the entire sequence, making it both space and time efficient, suitable for handling large inputs as required by the problem constraints. This is the Java implementation for the LeetCode problem KTH symbol in grammar, problem number 779. The logic mirrors the given Python solution, using a recursive approach to determine the KTH symbol. The base case checks if the row is the first row, which contains only 0. The parent value in the previous row is computed recursively, and the current symbol is determined based on the parent's value and the parity of k. Key Java-specific elements include explicit type declarations and the use of integer division for calculating the parent index. To solve the problem for n equals 2 and k equals 1, we start by making the initial call to KTH grammar, 2, 1. Since n is not equal to 1, we need to determine the value of the parent symbol in the previous row, which is row 1. To do this, we calculate the position of the parent symbol using the formula k plus 1 / 2. In this case, 1 plus 1 / 2 equals 1, so we make a recursive call to KTH grammar, 1, 1. Now, in this recursive call, since n equals 1, we've reached the base case, and we know the first row always contains the symbol 0. Therefore, the parent value for row 2, position 1, is 0. Returning to our initial call, we determine the result based on the parent value and the parity of k. Here, k is odd, and if the parent value is 0 and k is odd, the result is also 0. Thus, the symbol at n equals 2, k equals 1 is 0. Now, let's consider n equals 3 and k equals 3. We start by calling kthgrammar 3, 3. Again, since n is greater than 1, we calculate the position of the parent symbol in row 2 using the formula k plus 1 // 2. For k equals 3, this calculation gives 3 plus 1 // 2, which equals 2. So, we make a recursive call to kthgrammar 2, 2. In this recursive call, we now calculate the parent position in row 1. Using the same formula, k plus 1 // 2, we compute 2 plus 1 // 2, which equals 1. This leads us to another recursive call, kthgrammar 1, 1. At this point, we've reached the base case where n equals 1, so the first row's symbol is 0. The parent value for row 2, position 2, is therefore 0. With the parent value of 0 for row 2, position 2, we now determine the result for row 2. Since k equals 2 is even, we know that if the parent value is 0 and k is even, the result is 1. Thus, the symbol at row 2, position 2, is 1. Returning to row 3, we use this parent value of 1 to calculate the result at position 3. Here, k equals 3 is odd, and if the parent value is 1 and k is odd, the result is also 1. Therefore, the symbol at n equals 3, k equals 3 is 1. Finally, let's tackle n equals 4 and k equals 5. Starting with kthgrammar 4, 5, we calculate the parent position in row 3 using k plus 1 // 2. For k equals 5, this gives 5 plus 1 // 2, which equals 3. So, we make a recursive call to kthgrammar 3, 3. From the earlier example, we already know that the symbol at n equals 3, k equals 3 is 1, so the parent value for row 4, position 5 is 1. Now, we determine the final result based on this parent value and the parity of k. Here, k equals 5 is odd, and if the parent value is 1 and k is odd, the result is 1. Thus, the symbol at n equals 4, k equals 5 is 1. The time complexity of the recursive solution for the kth symbol and grammar problem can be broken down into two main parts. First, let's consider the recursive depth. The function kthgrammar calls itself recursively, reducing the value of n by 1 with each call. This process continues until it reaches the base case where n equals 1. As a result, the total number of recursive calls made is directly proportional to n. Next, we analyze the work done in each recursive call. In every call, the computation involves determining the parent index using the formula k plus 1 // 2, which is a constant time operation, or O1. Additionally, checking the parent value and calculating the current value based on k%2 also takes constant time. Putting it all together, since there are n recursive calls and each performs O1 work, the total time complexity of the solution is O(n). Now, let's analyze the space complexity, which depends primarily on the recursion stack. In this solution, each recursive call adds a new frame to the stack, and the recursion continues until n reaches 1. Because the function reduces n by 1 with each call, the maximum depth of the recursion stack is n. This means the memory used by the stack grows linearly with n, contributing O(n) to the space complexity. Additionally, the function only uses a small number of auxiliary variables, like parent and some intermediate arithmetic results. These variables require constant space, or O(1). Therefore, the overall space complexity is dominated by the recursion stack and is O(n). Comparing this optimized recursive approach to a naive approach highlights its efficiency. In a brute force solution, we would generate all rows of the grammar up to row n and then index into the kth position. However, this approach has an exponential time complexity of O2 to the power of n, because the size of the grammar doubles with each row, and storing these rows would also require O2 to the power of n space. The optimized recursive solution, on the other hand, avoids generating the full rows entirely. By leveraging the parent-child relationship between symbols, it reduces the time complexity significantly from O2 to the power of n to O(n). Similarly, the space complexity is reduced from O2 to the power of n to O(n), as we only used the recursion stack and a few auxiliary variables. This improvement is supported by the mathematical justification that the recursion depth is n, each call does constant work, and no additional memory is required beyond what's needed for the stack. In this problem, the best, average, and worst-case scenarios all result in the same time and space complexities. This is because the recursion depth is always n, regardless of the input values, and each recursive call consistently performs O1 work. Therefore, there is no variation in complexity based on different inputs. To conclude, the recursive solution is highly efficient as it computes the kth symbol without generating the entire grammar sequence. With a time complexity of O(n) and a space complexity of O(n), it represents a significant optimization over the naive approach, which suffers from exponential complexity in both time and space. This makes the recursive solution a much more practical and scalable choice for this problem. When tackling this problem, there are 3 common mistakes to watch out for. First, many people misinterpret the problem statement, especially when it comes to understanding the transformation rules or the recursive pattern involved. This can lead to errors, particularly for edge cases like n equals 0 or n equals 1. The solution here is to carefully dissect the problem's rules and use concrete examples to verify your understanding. Next, a brute force approach to simulate large sequences, such as when n is greater than 20, is highly inefficient. The sequence grows exponentially, which can easily exceed time or memory limits. Instead, look for repetitive patterns or mathematical properties that allow you to compute only the part of the sequence you need. Finally, ignoring edge cases is another frequent pitfall. Inputs like the smallest or largest values of n, empty strings, or other boundary conditions can lead to unexpected issues. Test your solution thoroughly with these scenarios to ensure robustness. Another challenge arises from improperly implementing recursion. Without optimization techniques like memoization, recursive solutions can cause stack overflow or excessive recomputation. To address this, consider dynamic programming or iterative methods to eliminate redundant calculations. Overcomplicating the solution is another area where candidates often struggle. Some may resort to using unnecessary data structures or advanced concepts when simpler approaches are more effective. The best strategy is to focus on the constraints and design a solution that directly addresses the problem. Now, in interviews, there are a few key aspects to keep in mind. First, always look for patterns in recursion or sequence generation problems. This can help you simplify the solution. Second, discuss trade-offs between brute force and optimized approaches early in the process. Interviewers appreciate clarity of thought as you transition from a naive solution to a more efficient one. Additionally, testing edge cases is critical. Explicitly show how your solution handles these scenarios, such as avoiding memory issues with exponential growth. Lastly, communicate your thought process clearly when deriving base cases, recursive relations, or iterative steps. This helps build confidence in your approach. To further enhance your understanding, you can explore related problems. For example, LeetCode 38, Count and Say, involves a similar sequence generation problem where recursive patterns are key. LeetCode 22, Generate Parentheses, focuses on recursive generation of valid strings, while LeetCode 46, Permutations, deals with generating all possible permutations of a sequence. LeetCode 118, Pascal's Triangle, is another example that combines recursive pattern generation with combinatorics. In terms of alternative approaches, you have a few options. The recursive approach with memoization is great for reducing redundant calculations, though it does require additional memory to store intermediate results. This is particularly useful when subproblem results are reused multiple times. An iterative approach eliminates recursion overhead and is often preferred for optimizing space usage, though it may require more careful index management. Finally, if the sequence exhibits a clear mathematical pattern, deriving and using a formula can be the most efficient option. This approach is fast and memory efficient but relies on the existence of a closed-form expression, which may not always be feasible depending on the problem. Great job! Today, we explored a recursive solution to kth symbol in grammar and discussed how recognizing patterns can simplify complex problems. Keep practicing, stay curious, and we'll see you in the next session. Thank you for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!